Okay, so we're going to look at how to apply the squeeze theorem. Now, one of the things that sometimes students struggle with in calculus is that we're starting to get into a situation where we have to do proofs. And there aren't that many in calculus that professors really require students to be able to replicate, but the squeeze theorem and using it appropriately does tend to be one of them. As you get more and more into mathematics, you'll have to do more and more of these proofs. But we haven't really been thinking about mathematics as a way of sort of reasoning, a way of explaining, a way of communicating. And so we tend to use it simply, particularly through algebra, as just a computational technique. And the goal is to get to the answer. And in real mathematics or more advanced mathematics, the goal is to explain yourself. It's to reason. It's to provide logical explanations for why something is true, not just to get to the answer. And so the squeeze theorem may be one of sort of your first exposures in calculus to that idea. And we see it in other topics like proving with the epsilon delta definition of a limit, where we have to care about the way that we're explaining things and showing the steps in a particular sequence. But this does take practice, and it is something that is sort of a new skill that students have to learn, and so it does take some additional explanation. The concept behind the squeeze theorem is really quite straightforward. If you have three functions, the middle of which you're interested in, and this middle function is bounded between two other functions, then when you take the limit and all at the same point, then the limits will have the same relationship as the original function. So the limit of f of x will also be bounded between whatever the values for the limit of g and the limit of h are. Now, this squeeze theorem is especially useful if these two limits on the end are the same value. Typically, they end up being actually 0. But as long as they're the same value, the squeeze theorem really does have a lot of use, because if this is one value and this is the same value, then there's really nothing else that the limit of the middle function can be except that one value in order to make this statement true. So we're going to consider a specific example and go through and show how the squeeze theorem works. And we're going to emphasize as we go sort of the kind of level of explanation that you want to provide, sort of showing your steps. And the goal is not so much just to get to the answer, which is important, but also to show the reasoning as to why that is a valid statement. So we have this function. We want to calculate the limit as x goes to 0 of x squared times sine of 1 over x. Now, this is sort of a typical example that we use the squeeze theorem for. The sine of 1 over x does not itself have a limit at 0. And so we can't use some of our other limit properties that we might have encountered in other types of problems. There's no way to algebraically simplify this. And so we're going to use the squeeze theorem, because even though the sine of 1 over x does not itself have a limit, it's actually oscillating more and more and more quickly as it gets closer and closer to the origin. The sine of 1 over x nonetheless is bounded. And so it's bound sine itself, the entire sine function, no matter what number you put into it, it can never be less than -1, and it can never be more than +1. And so we're going to say, since the sine of 1 over x is bounded between -1 and 1, so it can never be less than -1, it can never be more than +1, but it can be equal to either of those values. Then we know that negative Now, since we know that this is the case, then if we multiply the entire equation, this entire inequality through by x squared, then we will also have a true statement. So negative x squared is bounding x squared, sine of 1 over x, which is bounded by positive x squared. And you can think about this graphically if you want. If you actually draw the graph of the x squared parabola and the graph of the negative x squared parabola, you can see that our function x squared sine of 1 over x is going to be oscillating, but it's going to be oscillating bounded between these two functions. So we know that is true. And then we can say that the limit for each function will follow the same inequality. And so I am going to borrow, so I don't have to retype the limit all over the time. I'm going to borrow this. We're going to let the limit go to 0 in each one of these cases. Oops. And we're going to replace our g of x with negative x squared. And we're going to replace our f of x with x squared sine of 1 over x. And we're going to replace h of x with x squared. Now, while we may have a difficult time evaluating the limit on the inside function, we know that this limit is equal to 0. And we also know that this limit is equal to 0. Therefore, we can take our double inequality and we can replace both sides with 0. Now, the thing is here, this is why the squeeze theorem works, because the only thing that this value can be, this function can be, that would satisfy this inequality is if the function on the inside is also 0. The only way to satisfy this inequality is for the limit inside to also be 0. Or equal 0. Oops. Get it out of that. There we go. Now, again, the thing to keep in mind here is not so much that our goal was to get to, okay, the limit is 0. Woohoo! I mean, that's great. That is something that we want. But what a math teacher is expecting, what your calculus professor is expecting, is the explanation. So it's important to show all of the steps as you go. In a perfect world, sort of in a professional mathematics world, you would also want to provide the explanations. Sometimes students have a hard time with this because in mathematics, we tend to write the sort of equation stuff on the board and we just talk over the the explanation part and we don't write that down. But when you're writing on paper, you actually need to also provide, when you're doing a proof like this, you need to also provide the written commentary. So it's not because you're not there to stand over the thing and say, oh, well, the reason that this is true, the reason that I can make this claim is because of blah, blah, blah. But you need to write those explanations down. So ideally, you would want to use the squeeze theorem and not just show, okay, this step, and then this step, and then this step, and then this step, and then this step, and therefore bang, and then have no words. If you show all of those steps, that is definitely better than just jumping from maybe here to here, which I have seen people do. But instead, the sort of the goal here, and it's a good practice to get into, is to start writing down, so why can you make this step? Why does this make sense? Again, think of someone sort of in your class who's kind of at your level of mathematics, but is skeptical of what you're doing, and you're trying to explain it to them so that you write enough to justify the reasoning behind it. So it's not just naked symbols, but there's words and explanations that go with it. That's sort of the thing we haven't been doing in mathematics, in your mathematics courses through algebra up until this point. But now that you're getting into more advanced mathematics, particularly starting in calculus, and it will be definitely very true in linear algebra and discrete math if you go on and do those kinds of courses, where you're going to have to be providing explanations, where the whole point will be the reasoning. And you may not even write all that many symbols so much as appealing to theorems and writing out statements with just a smattering of symbols in the middle. So this is much more symbol heavy, but it really does, in an ideal situation, you want to provide the explanations, the reasoning in addition to that symbology.